Thank you for joining this session. My name is Kohei, not Shohei, unfortunately. So I have a nickname. Please call me Max. Yeah, take it easy. Yeah. So I work as an evangelist for IoT and AI at Soracom, and I'm an AWS hero. Yeah. So today, I will talk about a simple idea running generative AI on local device. So I think so you came here because you want running generative AI on your devices. So let me ask, so raise your hand. So has anyone tried running generative AI model on your device? No? No one? Okay. So another question. So did you think it's harder than I expected running generative AI on local device? Raise your hand. Thank you. So good. I feel me here. The pain points, so the reason I'm talking today, yes. Yeah. So one example is robotics. In this session, I will show design and operation at local inference architecture. I will also show when local inference works well. With a live demo robot arm, yes, you will compare the trade-off between cloud and local inference. So it works. Yeah. This is a rule-based, so traditional robot teaching. And so robot teaching now. And so latency, local device and cloud, and connectivity, and model updates. I will also show a practical way to deliver and update AI models at the edge. So to running generative AI safety and continuously. So here's today's agendas. So first, we will clean up the keyword physical AI. What is physical AI? So as the power of AI in the real world. And next, I will show the latency difference between local and cloud inference. So with live demo, yes. And after that, I will show how to update foundation model in local device with AWS IoT Greengrass. And finally, we will wrap up. So let's start. So what is physical AI? Physical AI means a machine can sense the real world with cameras, sensors, and can decide what to do and can act to change the environment. So with the growth and AI and robotics, AI moving from the digital world into the cyber world, real world. AI is no longer just just on the screen, it can move things in the physical world. We also use keywords, edge, so local, and cloud AI. So bottom, their ideas show how AI runs place. Edge AI runs near the data source, and cloud AI runs after the data goes to the cloud. So physical AI is a concept name. I think so, yeah. Physical AI is edge AI and cloud AI, so different layer. It's not about, about location. Physical AI is needed for three main reasons. The first is responsiveness. AI can react fast to what it sees and feels. It lets machine moving quickly when things change. The second is autonomy. AI can more than follow orders. It can think, act it by itself, and can learn the create new value. The third is collaboration. AI can understand human intent and work naturally with peoples. Humans and machines can act as one team and one goal. Here is one example of physical AI. Our customers, a company in Japan called Linkwiz, gives a robot arm vision by adding a 3D scanner. Robot arms are used in factories and production lines. So traditional robot arm use teaching. What means teaching is after slide. So they repeat fixed movements again and again. So if the object is in a different position or angle, the robot cannot pick it up. For example, if the robot set pick a flat object, so it cannot pick it tall one. Then human turns object so for the robot. Humans works so for the robot a little bit sad. Yeah. Linkwiz solution use a 3D scanner to find the shape and angle of the object. So use a camera. Yeah. AI understands it and adjusts the movement of the robot's arm. This scanner works as a robot's vision. Yes. And AI works as a robot's brain. This is a good example of responsiveness and autonomy, and collaboration working together. Here, so I will explain teaching. Teaching means teach a robot, teaching a robot. How to do that task? You can write a program, but so today's robots need complex moves. So as you see, so human moves the robot arm by hand, and the robot records the moving. The robot plays back, repeat task automatically. This is a traditional teaching. It's a core rule base. This robot arms is trained to pick an object on one spot. This one spot is a very well works. Oh, okay, yes. But object moves a little bit move. The robot cannot pick it up. So it examples fails. Why? Traditional teaching does not have vision. So rule-based method works well when the same task repeat many times and short time. In the case, manual positioning is required. So, but if the tasks is a little different, or if no human helps, we need a different approach. One solution is a VLA, so Vision Language Action Model. A VLA model sees the world with cameras and sensors, so understands the scene and makes the correct action. It expands generative AI from the cyberspace into the physical world. VLA is a key technology for physical AI. So the link with case is a good example of the VLA, VLA approach. By the way, so a model that understanding the text and images is called a VLM, Vision Language Model. Yeah. So here, a VLA model finds a black object and put it back at home position. You can imagine as camera, just a outside picture. So this yes. So it cameras capture table, and for the VLA model. The first, black object placed front of the arm. Oh, oops. Oh, yeah. I put it front of the arms. The VLA use a camera and sees it, pick it up, and put it back to home. Next. So I put a little bit different position. So rule-based systems is failed before, but VLA model works. These tasks run a Raspberry Pi and a simple web camera. So with AI, so physical AI is already possible in a very simple way. So let's compare. So large language model, yes, better understand the VLA. The first, LLM. It takes text and images input, so even code as text, and it output text and image. So yeah. So good examples. So Amazon Nova, Cloud, and GPT open source. Now VLA. It also takes text and images, but the data comes from sensors and cameras from the real world. At the output, the VLA is a movement generator. For examples, so RT2, so little robot, and small VLA. Here is the architecture of the VLA. A VLA model takes a real-world input from sensors and cameras. So it makes inference and generates action plan. So action plans send signals to actuators like a robot's arm, yes, this one, and moves a device. Some VLA can take a prompt text. For examples, so move the red apple. So another one, so pick the white block. With the correct training, they can do different tasks. Now, this brings a new question. Where should the AI run the inference? For a robot arm, it feels natural to run near, yeah, on the local device. But is cloud AI not useful for physical AI? Is that really true? So let's take a look. First, let's look at architecture. The difference between local and cloud is the side that VLA runs the inference on. With cloud inference, the device must send data to the cloud and wait for it to come back. So this round trip makes the latency higher. So what is far mean? So let's check it. So this demonstration. So here, two robot arms. So when one arm moves, so other arm moves in synchronize. Right now, they are linked, so USB directly, yes, via controller. So latency is very low. So Next, via cloud. So today's demos, so let's make latency. The synchronized signals goes out over LTE network and server send it back. So I use cat command, simple round trip. So switch to demo screen. Yes, I will. So this is Raspberry Pi 5. So I SSH to the Raspberry Pi. This is remote access service on Soracom. So it's a TCP port forward service. Connect. Yes. And I tried Raspberry Pi connect OS. Oh, my fingerprint. Yes. Oh, it's okay. Yes. So local operation fast run. So shortcut makes teleoperation local, but run the robot teleoperate command. Then now works. So it's okay. Hello. Yes. So via USB connect, very low latency. Just stop. Next, via cloud operation. So it's a bottom architecture I built. So I prepared reflector server on US East. It's okay. Yeah, this one is a reflector server. I tried socket command on reflector server. So connect. It's easy, great. And so what shortcut? I forget. Yes, reflector. Yeah. It's a socket command. So incoming TCP and outgoing TCP port. It's okay. So next. Raspberry Pi connects USB signals, TCP port. I run the socket command on Raspberry Pi, and two connection I need. Oops. And the login. This is upstream terminal, and this is a good downstream terminal. It's what command I forget is makefile. Socket upstream. Upstream and reflector server address is where is reflector. Oh, it's connect, yes. And I run the socket downstream command. Okay. So let's run the remote access. So let's try it now. So it's already slow, slow. So let's go, let's go. So it's okay? It's okay? Oh, okay. So let's move it again. This is a so LTE networks, USB signal, US East one, and LTE network and round trip. It's a delay. Yeah. Clearly delay. So compares on local. Yeah. It's okay to stop. So wrap up. So this is a backup video. So if my demo failed, so you see this screen. So I'm happy. So my demos works. So anyway, so as you can see, when latency appears, it loses real-time performance quite a lot. In this video, clearly delay. The latency is around 500 or 600 delay millisecond. Yeah. So of course, so if we use a nearby region, the latency can be much lower, and not all cloud calls take 600 milliseconds. Its key point is to measure it. So what does that latency really mean? 500, 600 is what is. Some say, so there is a 100 millisecond limit. When latency goes past that point, humans feel that something is wrong. For examples, so vending machine, the response time after pushing button on a vending machine. This is not everything, but a good reference for you. Yeah. If your systems acceptable this latency, then cloud inference is still possible. But you also need a stability connection to the cloud. So when do we need local, so edge AI? When should the device do the inference by itself? There is three main cases for local, so edge AI. The first, the camera and robot combination. The system must make a fast inference and a quick action. On a production line with one object, for example, per second. So very fast. If the inference runs far away, the object is already gone. Second, safety. When there is danger, we cannot wait for long latency, and we want it to work offline. This must be local. Third, privacy. As you know, so sensitive is a top security. Security is top priority. Yeah. For example, camera data is very sensitive, so it must be handled with care. One way is to keep the processing on local. If you think three cases similar to edge computing, you're right. They are almost the same. So up to now, talked about VLA and local, edge AI. And you may ask, which AI models good for local AI inference? So has anyone watched CEO keynote yesterday? Raise hands. Oh, great. So it's exciting and so funny keynote. So she said in keynote, models choice is critical. Yes, I agree. In the AWS cloud, Amazon Bedrock gives us many models. Yesterday, Google's Gemma 3 was released. So in cloud, choice and switch is easy. But on the device, model choice is still hard. Because the devices has limits. For example, storage size, memory size, and so on. We can install only one or two models. So what should we do? The answer is updatable. Today, latest AI models may be outdated tomorrow. So we must build a way to keep AI models updatable and always use the best one. So don't lock your system to one model, updatable. This is a core idea in the physical AI era. As you know, in the cloud, we already have Amazon SageMaker, Bedrock, and CI/CD pipelines. But what about the device? For real edge device, you must stay updatable. One of answer is AWS IoT Greengrass. It brings cloud-style updates straight to the device. And it turns a difficult challenge, hardware, into software, an updatable platform. Let's take a look. review AWS IoT Greengrass. So the latest version is V2. Is a Java-based software. It runs Linux and so other operating systems. In IoT Greengrass, applications are deployed to devices as component. And in V2, Docker container can be used as component as well. This lets you deploy and manage containers on your devices, much like Amazon ECS. Now, let me show you demos of updating a VLA model with AWS IoT Greengrass. Here is overall architecture. My VLA models stored a Hugging Face, bottom right, yes. So in the development environment, I learned Docker build to bring the model into the container images. Next, I pushed a container image to the Amazon ECR. Then I sent a deploy command through AWS IoT Greengrass. The devices run Docker pull and starts the container locally. Let's vote. So now change the screen demo. Now please look at my Docker file. It's a Docker file. Very simple. So 8 line, it's downloaded a VLA model from Hugging Face and bring into the container. This one. So the tag BB3, what means BB3 is a black box object. Detect black box object. So I have already this container image pushed Amazon ECR, this one. In Greengrass, this black object model is already deployed. It's a deployment, and what's deployed? It's a success in the component is this one. This is a container on the local device. So I'll show you the demos, but I would love to show the full demo with the here's robot arm, but actuator part will show the video. Sorry. So I appreciate your understanding. Yes. Anyway, so first, you can see the black object VLA model running right now. Start. Of course, VLA model finds the black box object and put it back. Right. And next, so another position. Of course, so right. VLA model find a black box object, catch to the and put it back. This is a before video repeat. Yeah. So let's update model. So white box detect model. So Hugging Face, another VLM model stored Hugging Face too. And I already so this is a Docker container too, and I edit Docker file. So black box instead white box detect model, right? So I run Docker build, black, not black, white build. As you see, so great. Docker image, yes, nice. This one. And push to Amazon ECR. So build command, so push, yeah. Oh, great, fast. It's okay, done, yes. And I create so IoT Greengrass recipe, use white box object model. So component, and now create version, and now using black box object to white, and this one white, and update. Oops. Oh, conflict version. So I increase version number and create version, and oh, it's okay. So this recipe deploy via AWS IoT Greengrass. Deploy next, and to the version increase, yeah, deploy. Let's check the Raspberry Pi. Now, process is now black object detect model runs. And okay, it's Docker pool, nice white object model container, and so slow, a little bit. Go for it. Yeah. Wow. What happened? Oh, okay, it's okay. Stop the black box object detect model, and so change the white box object detect model. It's easy, yes. So actual part is a video. So after the update, it works like this, yes. So it detects the object in front of arm, and of course, so it detects it even in a different position. Yes, this is a success, and same as black box demos, different position. So VLA finds it and put it back. Another one, this new VLA model is designed so detect white object only. So even with other objects around, it pick up only the white one. Look, it's a so detect white box object and catch. Okay, oops, it's very cute. And so put it back. So of course, so change so object position. It find and so catch. So put it back. It's okay, yeah. So you can update the model or switch a new VLA model if the system is updatable. With Docker, you can export device files. So you can use the cameras and so sensors you can inside use container. So and please remember, so an AI application that cannot be updated becomes old very fast. AI needs not only code and data. It also needs the model files. So using IoT Greengrass instead of making your own systems helps the system stay stable. In IoT device development, we used to work only with program and data. But now we also work with AI models. There is two important points. First, the network environment. You don't need constant connectivity, but deploying AI model and update AI model, fast and large data transfer network. So indoors, you can use Wi-Fi, but outdoors, when Wi-Fi not available, one option is LTE. So my company, Soracom, provides mobile connectivity for IoT and AI. And today, I shared our experience with you. Another one, so you can use broadband satellite network, like Amazon Leo, yeah. So connectivity is important. So second is file size. AI models are very large, so we need new knowledge to handle them. So even, yeah, okay. Even a small model is about 1 gigabyte. It's a huge. So open VLA model over 15 gigabytes. So we consider this big, large model deployed. In AWS IoT Greengrass, there are 3 ways to deploy large files. First, you can use IoT Greengrass artifact files. It's simple, but it has limit, so 2 GB limit. So second, you can put the model file inside Docker container. This is a method so today I use. So the limit depends on Amazon ECR. So 3, you can download the file so with a script in the IoT Greengrass recipe. This is so avoiding most limits, but you must check the download and so execution yourself. So choose it right method. So based on the file size. So my recommendation is so bundle the AI model in the container. As you saw in the Docker file, is so very simple. Bundle the model this way. Containers makes so development and testing much easier. So AWS IoT Greengrass can also manage them well, and this helps so avoiding file size limit. We still need some skills to keep the container, so containers layer small. So today, so showed you many things. We looked at the idea of physical AI and how to choose between local and cloud AI. Physical AI is not only edge, so local only. Cloud AI useful, so physical AI. If the latency is acceptable, the cloud works very well. The key point is measurement and requirement. So you remember, so 100 millisecond barrier. And so for physical AI, the most important idea is keeping it updatable, not just choosing models. You don't need to build updatable systems from scratch. We have IoT Greengrass. Today, you saw how AWS IoT Greengrass makes devices updatable and reliable. So AI will continue to grow and maybe so new normal. Let's use its power in the real world, so with updatable local and edge AI together AWS IoT Greengrass. That's all from me. So my bad English, but so thank you so much for joining this session. Thank you.